LED lights are everywhere, and that gives us a great opportunity to use these LEDs to communicate wirelessly. So we can build LiFi systems to cover a space. The advantage is that the signals do not go through the wall, such that we do not have interference from other locations. But the question is, how green are these systems? How energy efficient are they? And we like LEDs because they are so efficient. 200 lumens per watt. Well, what may be quite relevant at this moment is also what is the quantum efficiency. And the quantum efficiency of LEDs is pretty large. So now the question is the quantum efficiency when we use LEDs for communication for LiFi also this large? And the outcome will be that the quantum efficiency for illumination is not the same as the differential quantum efficiency when we talk about communication. Because in communication we already light up the LED, and then the question is, if we have one more whole electron pair that recombines, does that always give a photon, or is it quite often the case that there is no photon generated and that we basically only lose the energy? And the outcome of some math is that there is a difference in the efficiency for illumination and for communication. What is quantum efficiency? Well, it's the ratio of photons generated within the active region of the LED compared to the number of electrons that is injected into the quantum well, injected into the LED or into the laser. And in the differential quantum efficiency we just talk about differences. One more whole electron pair, one more photon relative to the DC bias. So let's have a look into what is happening inside the LED. We have holes and electrons coming in. A hole and an electron pair is generated proportional to the current. And of course the charge of one electron is Q, and therefore the change, the difference of the number of holes and electrons, the N dt, is equal to the current divided by small q. And N is then the number of holes and electrons. But that would be the case if the LED just acts as a capacitor. But there is also a recombination inside the LED. Holes and electrons recombine, and that is a function of how many holes and electrons there are. So let's write out the full differential equation. The change of the number of holes and electrons, the N dt, is the current that goes in minus all the recombinations. And there we have an A, B and C term. The A term is the SRH recombination. Shockley, Reed, Hall were the people who first wrote about this effect. It's non-radiative. So this A times N, the first term here, is a loss effect. But it's only relevant if N is relatively small. If N is larger, if we have more holes and electrons, the B term and the C term become more important because there's N square and there is N cube. B times N square. That is when a hole and an electron find each other and a photon comes out. That's a recombination, and that is proportional to the number of holes and electrons, so there is an N squared. If we drive the LED more and more, we put more and more holes and electrons in there, then the efficiency goes down. So the third term, the Auger recombination, the C term, is a loss term. And quite often engineers call that the droop of the LED, and becomes particularly relevant if we go too far. This story is relevant for illumination. For communication it's a little bit more difficult. Then we have to split the total signal, the current for instance, I of t, in the DC term, plus a small signal variation on top of it. The large term IDC I write with a capital, and the small term, the small modulation, with a small print symbol I. And we can do the same decomposition for N, for the number of holes and electrons. N is a number of time, is a function of time if we modulate. NDC is the DC bias level, and on top of that we do a small variation, small n of t. And I can write these terms into the expression, into the rate recombination differential equation. And then the change of n is proportional to the current that comes in, plus, and now I have to take care of all these terms. The DC term plus the small signal variation. But if I write out this full expression, I can just take out the terms that are relevant, that are large enough to consider. And then we could say that small n is much smaller than capital N. So I only take the first order terms, looks like the first term in the Taylor expansion. And yes, there is a second order term. Yes, LEDs are nonlinear. There is distortion, but for time being we assume that that is relatively small. So I can do that decomposition for the DC, and I can also do it for the modulation signal. And if I do that, I can write and I can define the quantum efficiency for both cases. What is quantum efficiency? The ratio of photons that come out over the total ratio of holes and electrons that recombine. So it's the B term divided by all these terms. And for illumination it's B times n squared divided by the whole expression A times n, B times n squared plus C times n cubed. That's quantum efficiency. If we talk about small variations, if we look into the expression for the small signal, we have 2Bn, that's the term proportional to the signal that is being modulated and that results in photons, divided over the rest, and that's A times 2Bn plus 3Cn squared. And what you see here is that this is a different expression. So the behavior for modulation and the quantum efficient there is different from the behavior for illumination. So if we optimize an LED for illumination to be as efficient as possible, to be as green as possible, that's not necessarily the way of operating the LED for communication. And if we want to optimize our system, this is something where we see some difference between the two. I plot these as a function of the current through the LED, and you see that, well, if we take care about 10–20%, then definitely there are major differences. But anyhow, it's good to consider this when you optimize the LEDs, and also to consider this when we talk about how we should use these LEDs. Quite often you can make a choice. If you need more light power, you can add a second LED, run it with the same DC bias, with the same signal. We get twice the power in, we get twice the light output out. Or we could just use the single LED and feed it with a stronger current. And then of course the question is, what happens to the efficiency? It may become better, it may become worse. So in all these optimizations, it's interesting to see how we should optimize this. And I've read many papers, many scientific papers, that focus on bandwidth. We like LEDs that have a huge bandwidth because then the bit rate that I can achieve is huge. And indeed, you may have read the papers by Shannon. The throughput, the capacity, is proportional to bandwidth times the logarithm of signal to noise ratio. The logarithm of the power that we create. The logarithm of the efficiency. So why care about efficiency if it's all about bandwidth? The problem is, you should not rely in this case on the Shannon equation. Because the LED acts as a very gentle low-pass device. There is not a brick for maximum frequency. It's not a brick wall like in radio communication where you cannot exceed a certain bandwidth. If you increase the bandwidth, if you go through the 3 dB bandwidth, you get a little bit more attenuation. And you can still achieve a lot of throughput at these higher frequencies. So, if you read some of our papers where we go into this in more detail, the throughput of OFDM is dependent on the bandwidth of the LED and on the signal to noise ratio, but they are at least equally important. Let's assume that we have weak signals. Then basically the number of photons per bit count. How many energy do I have? And it's not limited by bandwidth, it's limited by signal to noise ratio. But then you may expect that if we have a strong signal, it all depends just on bandwidth and that we don't care so much on the signal to noise ratio. But the challenge is, if you consider this from a signal processing perspective and you optimize the modulation, you could use that stronger signal and go for a wider bandwidth, simply because we can push through the 3 dB bandwidth and just pay the penalty of having a somewhat weaker signal because we have more signal. And then it turns out that the rate is more or less proportional to the signal power raised to the power 2/3 multiplied by bandwidth to the power 1/3. So the rules of the game are very different if we talk about LEDs or for a strictly band-limited radio channel. And then it of course becomes relevant to talk about what is the bandwidth of the LED, how can we improve it, should we go deeply into droop? Well, if we push more and more current through the LED, the radiative recombination increases, yes, but the droop grows much faster. Many of the holes and electrons recombine in a non-radiative way. You just lose energy. Yeah, the LED responds faster to fluctuations in the current, but that is all because so many holes and electrons are lost because they recombine very rapidly because of this droop effect. And that all makes it a very interesting optimization. What I hope to have explained is in intuitive terms how this all works. And if you really want to know the details, of course we've published that in scientific papers. If you want to approach it from communication theory, then an interesting paper may be the one that we published at the International Communication Conference in 2022. If you like to address it more from a photonic side, then the LED assessment based on an improved quality factor for LiFi communication was presented the same year in San Francisco at the SPIE Photonics West Conference. And the tutorial is in IEEE Communications magazine, and we called it Wireless Communication over an LED Channel. Yes, there were colleagues who said, it's not an LED channel because the channel is the propagation channel. No, if you look into it from an information theoretical perspective, then the limitation of the channel, the thing that really matters in between the transmitter and the receiver, is the device that matters most, which in this case is the LED. So that's why we dare to call it the LED channel, and that's also how IEEE Communications magazine published it.